Okay, welcome everybody. So this is MVCC part 2. Just a brief recap. We started with this kind of mapping in our store. So object IDs map to a list on one side, a list of committed values, and this one, a list of objects. We started with that, but then we extended that to have validity entries and the work in progress version. That's the basic mapping done in a key value store. We talked about that last week. And we extended that to have these version entries. So we have a start validity. So for each entry, we need to know starting from which point in time is it valid. There's no end point in time. There's just a start point in time. And that's the start validity here. Yeah. Then is the actual object. That's the value. And then there's a flag whether this entry was deleted. So we had that discussion last time already. So there are two types of changes you can do to an object. That is either you insert it, so you enter a new mapping from object ID to an object. That's an insert. If it didn't exist before, that's an insert. You update it, which means there is already a mapping from an object ID to an object, but you change the object somehow. That's called an update. And the third is you delete it. And deletion is done here not by removing anything from the store, but by marking it as deleted. Yeah? That also has some ramifications if you think about GDPR compliance. Nowadays, you have to be super careful when and how long you're allowed to keep data. You have to delete data. You have to guarantee deletes. Users have the right to ask for the deletion for the data. Yeah? You have to be very careful, in particular when backups come into play and replicas of your database system, stuff like that. So this is something to watch out for. Yeah? If you never delete this stuff, you might be violating GDPR. But so that's the basic structure. And then we extended this internal representation to something like that. Now we have a list of committed entries of type version entry. And we have a work in progress entry. That may be none, signaling currently no one is updating, inserting, deleting this stuff, this entry. But at some points in time, some transaction might be working on that. And then you have an entry that's not none or null. We will look at that in detail later on when we walk through examples. Today we will be looking at a lot of code. So that's the example I showed. And here we have a validity start. Yeah, then we have a tuple. So here this is a relational kind of store. And then we have a flag. And if you wonder how this can be 9 and this can be 8, we will get to that. Yeah? So this basically is just the start of a transaction. Yeah, and it doesn't mean that the entries here, it's still possible in this world that you have a work in progress entry from a transaction that started earlier, but another transaction that started later, that is 9 in this case, and committed an entry. So transaction 9 already committed, 8 is still running, and 8 started before 9 obviously, so that's may yield to that confusion, that may lead to that confusion that we have a 9 already here, but still an 8 in work in progress. That's possible, actually, in this world. Okay, here we talked about isolation. And then these 3 phases, they are important. So again, phase 1 is the simulation phase, where the transaction is working in its bubble, on its private copy of the database, its private snapshot. Yeah, that's what I used my phone for last time. You do a snapshot of the data, a read-only snapshot, like a picture you take with your phone. And all the changes are also in the private bubbles. You don't touch the main database version. Yeah? You don't touch main on Git if you wish. You do it in your private bubble, your private feature branch. But then once you want to merge into main, like in Git, you have to make sure there are no anomalies, no isolation problems. And that happens in validation. Yeah? Validation checks that you didn't violate any isolation properties. And yeah, then we proceeded to look at that. And basically, we looked at these read-write conflicts and the write-write conflicts. I'm not going to repeat all of that. Important for the write-write conflict is you detect write-write conflicts already in phase 1 in the simulation phase. Yeah? If there's an entry, a work in progress entry by one transaction, and then another transaction comes in and wants to change the same object, that second transaction will be halted, will be suspended, will be aborted, however you want to implement it, but it's not allowed to also change the stuff. You already detect, oh, there's a write-write conflict. So that happens in phase 1. And yeah, as long as you guarantee these two invariants, everything is fine, and that's actually what our implementation is doing. Read-write conflicts are a bit more tricky, and then we again reiterated, the read-write conflict can be per object. Two transactions touching the same object somehow. But that's the easy case. The more involved case if you read from the store using a predicate. So you don't have a key lookup. You don't say, I want to have object ID 42. You just say, I want to have all objects where the A attribute is 42. Yeah, and that may be 0 to many objects. And this is still reading those objects. So on that level, you can still have a read-write conflict. Yes? This leads in the undergrad lecture, we had the discussion, and there this leads also to what's called a phantom problem. Okay, so much about the repetition. Yeah, and then we started with the validation algorithms. I think I can jump directly to the code there. That's what we do. So there are two kinds of validation algorithms, but before reiterating those algorithms, let's dive a little bit into the code today. As promised, there will be slides, but there will be way more code than slides. I have a nice shortcut for all these methods. So the key value store we looked at. So let's look at some method of this transactional key value store. This inherits from this non-transactional key value store. And we have a couple of things to look at here. So one is that for all the transactions that are currently running, I keep an extra dictionary that's called the transaction dictionary that collects information about the transactions that are currently running. And one is the read clauses. So all the where clauses you ever use from a transaction are stored per transaction. So whenever I want to have the information which read clauses were used by a specific transaction, I can do that. The store collects that information. And that's important for the validation phase later on. Yeah, I can also keep a write set, depending on what kind of validation I do. So the write set is a set of object IDs this transaction modified, be it insert, delete, or update. So that's a set. In our implementation, we restrict object IDs to strings. You don't have to do that, but it makes life a bit easier here. Then there's a committed timestamp. This is initially none, but once the transaction commits, it gets a timestamp as of that time when it commits. Yeah, that is saying, okay, now it's committed, successfully committed, validation was successful, the changes of the transaction made its way into the main version, and now you get a committed timestamp. Yeah, and maybe the last we can look at later, that's an optimization we do. Yeah, so this is a constructor. Here you basically see a parameter allowing you to change which validation algorithm to use. So in the slides you see validation algorithm 1 and validation algorithm 2. And that's basically the parameter. I also wrote it on the slides here. Yeah, that's basically if you set this to true, you will use validation algorithm 1 in the store. If you set it to false, that's the next slide here, then you use the second validation algorithm. Actually, when discussing it yesterday, we came up with the validation algorithm 3 and 4. Don't worry, I think 2 are enough for a moment, yeah? So don't be afraid. But anyway, if any of you is interested in writing a thesis about MVCC, so we're discussing that almost every day, and we find interesting things and observations and things one could try out. There's really room for making investigating a couple of ideas we have in that space. Okay, right. So here we initialize this dictionary, the transaction dictionary, for short self-TD, that maps from a transaction ID, which is an int, an integer, which is this timestamp I mentioned. Yeah? We don't use time as state and time or something like that. We just have this strictly monotonous integer domain, which and every transaction that starts will get such an ID. You will see that in a moment when we look at begin and commit methods. And then we have such an entry. Yeah? So for each transaction that's ongoing, we keep such an entry in the dictionary. We also keep a log of the committed transactions. So whenever a transaction commits successfully, we append it to a list. And here the list is important because we need the order at some point. A set wouldn't be enough. It wouldn't keep the order necessarily. So it's a list that keeps the transactions that committed. Okay, so how do we start with that? So maybe we look a little bit more at the user side. Maybe I show you a little bit how to use this stuff. And how to use that stuff you can easily look at when you look at the tests. So we have test stores basics. Maybe we start there. This is, maybe we start here. Yeah, so those are unit tests I implemented. And basically what these stores, how to use these stores. So I test here at the same time this non-transactional key value store and the transactional key value store. So I loop over that. And basically what you do is you you bulk load it with some fake data. So this helper method, if you go into that, just creates 100 tuples. Yeah, this is using a library called Faker. That's super useful. Yeah, so this Faker library allows you to create fake email addresses, fake names, countries, and whatnot. It's super useful to test your code. So in general, when you test a database application, any application using a database, it's super, super, super important to have fake data for your unit tests. If you test it without data, you will miss everything. It doesn't make sense. So here's a list comprehension I'm using. So basically saying for the number of tuples, I create a couple of instances of this stuff. Stuff is just basically a relation with two attributes. So two fake ints I'm creating in the range up to 1,000 and up to 2,000. That's all I'm doing. So this is just creating some fake data for the store. Yeah, and then of course, in every unit test, you have a couple of asserts. So I just assert that the size corresponds to what I'm expecting here. And then I do a couple of checks here. Maybe that's not so interesting because it doesn't show the transactional features. Maybe we directly jump into the begin transaction. That gives you a better idea on what's going on. Here's a better idea on how to use the store. So basically as a user, so the user being someone who uses the store would create an instance of that store. And then at some point, whenever you want to run a transaction on the store, you call begin transaction, obviously. And the begin transaction method returns an integer, which is the transaction ID. Yeah, that is a unique ID being returned. So when you look at what this method does is, maybe I think that's a good way to start. So you get the next transaction ID from the store. This has to be synchronized. You mustn't do this concurrently. So these IDs have to be unique. So basically, you have an internal counter in the store that whenever this method is being called, you return the next transaction ID. So your number of incoming transactions with those IDs, and they keep on increasing, and they are pairwise disjoint. That's what happens here. Yeah, so you get this next transaction ID, and you add an entry to this transaction dictionary. Yeah? Begin transaction means, aha, now that the store is aware of there's a transaction going on, and you add metadata to the store. Yeah? So basically you say, okay, the read clauses is a set, the write set is a set, there's the committed timestamp is none, didn't commit yet, and this you can ignore, that's an optimization. At the end of the day, you return this next transaction ID, and that is what you can then use as a user of the store. That's what you get here. Yeah, then you have a couple of asserts here I'm doing. This is a very basic test. Maybe look at a more involved, basically. But then, okay, maybe let's look at the counterpart. Yeah, so if you have a begin transaction method, there's a commit transaction method. And if you go into this, you see, aha, he will see the phases that you also saw on the slides. Yeah? So the first thing and the first trick we are playing is we again draw an ID. Yeah, we get an ID that will be the commit timestamp, and no other transaction has this commit timestamp. Yeah, so we get such an ID from this getNextTransactionID method, and then we run the validation phase. Yeah, so that's this method, this helper method. We will go there in a moment. And then you either get validation is successful or it's not successful. And if it's not successful, well, yeah, then you have to abort that transaction, which comes with, maybe we go into that a little, let's look at the high level. And basically here the method will exit and will raise a transaction aborted exception. If validation is successful, however, you can enter the actual commit phase, which means all the changes this transaction did, all the work in progress changes are now moved over to the committed list. Yeah, that's basically what we had on the slide here. When we go back to the slide. I think I had it. We looked at these three here. Yeah? So this commit phase, phase number 3, yeah, that's where we are. If the transaction passes the validation phase, we move all work in progress changes over to the committed version list. Yeah? That's all you have to do. Yeah? The hard part is validating. If you're done validating, you're confident, then you can move these entries over. Okay, so we go here again. And that's where we are here. So that's the commit phase, so this third phase of MVCC. There are tons of asserts here. Of course, you can argue, you can also switch them off, I guess, in Python. But I highly recommend in coding writing asserts wherever possible. You can also write a comment after the assert with a comma. So if the assert false, you get more informed information why the assert false. But typically when coding, it's really like you have all of these asserts in your head anyway. Yeah, you make assumptions about, when I'm here, I must do this, or this must be true. Yeah, then write it down, write it down. It's so much better in debugging things. Yeah? Because the effect is you can, the space where the error actually occurs is restricted then. Yeah, typically, sometimes you have errors that are, you don't, where the heck did that happen? Yeah? And then you spend a lot of your time just tracking down, okay, it's this module, it must be this function, it's this part of the code, or it's this line. And by asserts, you get the warning early on when you screw it up. Yeah? And that restricts the space or the number of lines you have to check. Yeah? So I highly recommend that. And the argument, it's too inefficient, no. It's the trade-off is really functional correctness here, that if you fix that, that's the most important thing. Yeah. So maybe we look at these three methods first. Yeah? From the outside, we will now approach how that works in the store. So begin transaction, commit transaction, and abort transaction. So if I look at begin transaction, that's basically the easiest method here. So the only thing that happens, as said before, we get this transaction ID for the transaction, we return it eventually here, and we do this entry to the transaction dictionary. That's everything that happens. So if you want to abort a transaction, that's also relatively easy. Okay, so the abort transaction may be called from the user or may be called actually from the store or from the database system. But basically what that means is that you kill, you have to remove all the work in progress entries from the store. So in our implementation, we keep a so-called write set, which means whenever we touch any object ID, we put it to this write set. Yeah, so I updated, deleted, inserted object ID 42, okay, I added to the write set. So at the end, so at all times, the write set is a set of object IDs, this transaction modified. Yeah? And with that, I can easily loop over this write set in an abort transaction method and simply remove it. Yeah? So here by setting it to none. So here, I don't have to worry about freeing memory and segmentation faults and all of this stuff you have in C++ is fun. You don't have that here, you just set it to none. It's handled automatically. And this has multiple effects. So the one is the changes done by this transaction are removed from the store. Yeah, whatever this transaction, that's basically, so again, if you look at the asset properties, the A, asset meaning everything is done of the transaction or nothing. I'm aborting, so none of the transactions must find its way, their way in the database. Yeah? And that's what's happening here. So I'm removing all of these changes. And the second effect is, once I did that, once I set it to none, other transactions are now allowed to change it again. So if I set the object ID 42 to none, before no other transaction could change it, because the store will always check, oh, there's already someone working on object ID 42, then I'm not allowed to do that, I have to abort. Yeah? So one writer at all times, that's this rule. And we check it in the implementation via this work in progress entry. Postgres, for instance, does the same thing. Yeah? So if they do an explicit lock on a tuple, and if there's one writer, the tuple is locked for writing and others can't write it again. It's the same thing. So the same idea, multiple readers, but only one, at most one writer. Yeah, and that's all you have to do, basically. Yeah? You could then argue, okay, from the transaction dictionary, you also remove the transaction. We don't do it in this implementation. Yeah? So you could also run the transaction dictionary as the ongoing transactions only. And maybe you want to do that in a real implementation in C++, because of course the transaction dictionary will get huge if you never delete the old transactions that are inserted there. Yeah? So in all of MVCC, you have to be careful to delete data at some point in time. I would like to postpone that discussion for a moment because it makes things unnecessarily complex. We touched that briefly already last time when talking about the different versions in the committed list. Yeah, the committed list has all these versions. And why the heck do you keep the old versions if no one is using those versions anymore? Yeah? So at some point you can delete old versions. I mean, you never delete the most recent version, and you never delete versions transactions are still operating on their snapshots. But if there's a version no one is interested anymore, you can safely delete it. Yeah, and that's fine, because any new incoming transaction will get the most recent snapshot. Yeah, so if someone is reading an old version, this can only be because it's an old transaction. When that transaction started, that old version was the hottest stuff in town. Yeah, but that's not true anymore. Now it's old crap and outdated. Yeah? But once these transactions are aborted or commit these old transactions, you can, no one is reading the old versions, you can delete those versions. So you have separate processes, separate logic for that. Again, in Postgres, you have funny names like vacuum. There's a vacuum process regularly cleaning your database from all of this stuff. That's how it works. Okay, and here's the same for the transaction dictionary. Okay, now we have a begin transaction, we have a abort transaction. Let's look at commit transaction. So as I said, we get this timestamp for the committing process. We run validation, yeah, a separate story. And if it's not successful, we throw an error, okay. If it's successful, again, there's a similar loop as in the abort. So we loop over the write set, we loop over all objects this transaction touched. And then what we do is a couple of asserts, but basically the only interesting thing are these two lines. So this is moving the work in progress entry to the committed list. Yeah, so this is my work in progress entry from this transaction. I get it here. So from the key value store, I get this work in progress entry here. So this is the work in progress entry this transaction created in the store. And I append it directly to the committed list. Okay, that's what's happening here. And I set this work in progress entry to none. So this is kind of still, yeah, okay. Okay, this maybe I should also mention. Okay, there's a little thing you have to do here, otherwise you will screw up your store. You have to start the committed timestamp. Yeah, so If you remember, there's a committed timestamp that's initially none, so unless the transaction commits. Now we have to, okay, what is the validity of this entry? And the validity is the committed timestamp, and that's basically the number we drew here. Yes, this is this point in time. Yeah, this point in time, that's so what happens at this point in time is committing this transaction. That's the only thing that's happening. And the version entry now gets this validity, yeah, start time, and that is basically this number. So this entry in the committed list will get that value with entry.start validity, and then we append it to the committed list. Yeah? And now this entry has exactly the committed timestamp as of now. And then the same thing happens here. So we have to delete the work in progress entry, just like in the abort operation. And then this work in progress entry can be used later on by other transactions again. Yeah, then you append, so you mark it in the transaction dictionary as committed. Yeah, you keep track, and this transaction committed, and you can differentiate between transactions that didn't commit and committed. And eventually you also append it to the log of transactions, but that's for later use. That's basically what commit is doing. Yeah, is that clear? Any questions? Okay. So far so good. So where were we? Commit transaction, begin transaction, commit transaction, abort transaction. Okay, I think then we should, so here these underscore methods are all helper methods, internal methods, and I will now focus on these external methods. That's basically the API the store is using. And as a user, someone who wants to execute a transaction, okay, you need begin transaction, you might need abort, you definitely want to use commit. Those are the three wrapper methods, so to say, wrapping the transaction. But then in between you want to do some stuff. Yeah? So what do? You can read an object, you can update an object, or you can delete an object. Yeah? That's basically the three things you can do. And let's start by reading something from the store. How does that work? So the read method, all of these methods require you to pass a transaction ID. So the store has to know who the heck is trying to read some object, because the store has to provide you with your bubble, with your snapshot. Each transaction operates on the snapshot, so the store has to know. Yeah, and the store has to know that you read a particular set of objects. That's very important for the store. And reading in our implementation is already done via clauses. So a where clause, like in SQL, a where clause, basically a predicate saying, okay, I want to have all the objects from the store that fulfill this predicate. This is something you can ignore. Yeah, I think so. From a high level, what this method is doing, other than checking, yeah, maybe the transaction ID should be in this transaction dictionary. So if it's not in the transaction dictionary, this means you send a read objects call without a begin. Yeah. So if you called this method on a transaction ID that's not in the transaction dictionary, then you get an error message. That is what this line is doing. Or if the committed timestamp is not none, that would mean you would call read objects on a transaction that already committed. Shouldn't do that. Not a good idea. Okay, and then basically that is how I explained it on the slide. So here we read a snapshot. Yeah, we read the snapshot of the data for this transaction ID with this specific where clause. Yeah? And then we basically return the result. That's all we do here. Here already you see code I'm using for this validation method. So while reading the data, I pump all of these objects through a checksum. So all the set of objects I'm reading, including all of their attribute values, the entire byte stream of those objects, is pumped through a checksum. And I keep that checksum for the validation algorithm 1 in this transaction dictionary. So the transaction dictionary not only collects the read clauses, that is the where conditions, but also the checksum I observed in my bubble. So while reading this stuff under snapshot isolation in my bubble, I saw a specific version of that data. And that version will create a specific checksum. Now, if I re-execute this where clause later on a different version, it may happen that the checksum differs. And then I'm in trouble. We will go there. Yeah? So I will want to make sure that the checksum is the same. In other words, when I re-execute this stuff later on in validation, I want to guarantee that everything I read is unchanged. No change must have occurred, because those changes may lead to isolation anomalies. Yeah? So that's for validation. The basic thing of this method, however, is, or the basic effect is, yeah, you read the snapshot of the data. Yeah? That's what's being done here. Okay, before diving into that in more detail, so that's the read objects. Then there is, let's start with update object. Can I make this a little wider? Yeah, these typical checks. So everything is commented. You can also go through that back home, I guess. The checks created. Yeah, this is again this problem I mentioned last time already. So if you pass something by reference, and that happens here. So you pass an object. So what you're trying to say here is, okay, so I'm transaction ID 42, and here's my object ID, and that is a new version of the object. That's what you're saying. So transaction 42 object, is trying to update object 7. And by the way, that is a new version of the object. That's the 3 parameters you pass to this function. Yeah, then you do the typical checks. Hey, is there even a transaction with this transaction ID? Otherwise, this doesn't make any sense. You must make, that's here now, the check is happening, I mentioned several times. Oh, check, there's no other ongoing work in progress version here. Yeah? So here we check in the key value store that this work in progress entry is either none, so no one else is touching this object ID, or it has a start validity that is equal to myself. Yeah? So here the condition is the inverse. So if the start validity belongs to a different transaction ID, that means someone else is updating the object, then you must stop, then you must abort, you must hold. Yeah? In a C++ implementation, or if you extended our implementation, you could also say, okay, I could also stop the thread. The thread could wait at this point. You don't have to directly abort it. You don't have to directly raise this exception in this line. Yeah? But for simplicity, we just say, no, abort it. It doesn't work. Yeah? So those are the checks you have to do. And that's basically, this is exactly the point where you avoid write-write conflicts. Yeah, that's the point in the code. Write-write conflicts is avoided here. So you are only allowed to write if it's either the work in progress is none, no one is touching it, or you already updated it yourself. This could happen. The transaction updates the same object multiple times. Yeah? And that's what this second check is about. Yeah, okay, so we're good. So we pass these checks. Okay, then we create a new version entry. For the moment, we have a start validity of this transaction ID. That will be used here by other transactions as I touch the work in progress entry. And we do a deep copy. Again, deep copy to be on the safe side. I mean, you can also put more thought on that in C++ in particular, because you would always copy the data at this point in time. But here, to be on the safe side, I copy it because I pass it by reference. If I pass something by reference, the updated object, I pass it to the store. The store changes it. The store performs the update. And then from outside, you still have the reference. And you still change the stuff. You're completely screwed. Yeah? If you ever did that, you have to do that in C++ or any language to feel the pain that comes with that and detecting the stuff. It's really, really painful. Yeah? So to be on the safe side, I say, no, I do a copy. I don't care what you do outside with your reference to the object. I do a copy. Yeah? So this is now my data, and no one else has access to this copy of the data. It's very important. It's very stupid error situation that can occur otherwise. Yeah? So the implementation is always, that's also in more didactics, I try to, in doubt, I make it simpler, yeah? Because I want you to learn this stuff. You can do tons of optimizations in MVCC. And that makes it sometimes hard to learn this stuff when you look at other implementations or other explanations. Yeah? I try to get rid of all of these things you don't need. Yeah? That's just reducing it to the very core. Okay, so we're almost done here in the update method. So now we have this new entry created. Yeah, and then the work in progress entry is assigned. So this is assigned to this variable. And then also we add it to the right set. So we keep the information here that we touched, that this transaction, TAID, touched this particular object. Huh? And every time we update an object, we do that. As you saw before in abort and commit, we loop over these things to move it over or delete it. Yeah? So that's very important to keep that information. That's all you do to update an object. And then delete is very similar. So what do we do in delete? So here you don't pass a new version of the object, doesn't make any sense. Yeah, you just say, aha, it's my object ID, that's what I want to delete. And then there's the transaction ID, that's the caller deleting the object. Again, you do these checks, is that even in the transaction dictionary, and so forth and so forth. It's the same check as before. Is that so if there's, so either work in progress is none or it belongs to this transaction. So if you're good to go, here we create a new entry with deleted equals true. So marking that this is deleted value is set to none. Again, you could also create subtypes of these version entries. So you could, for instance, have an abstract version entry class and then have subclasses. For instance, one for insert and update and one separate subclass for delete, because a delete doesn't make really sense here. It could also signal the value, doesn't make any sense for a delete entry. You could also have a subtype that doesn't have that attribute if you wanted to do that. Yeah, that's another way of doing it. We did it like this. Yeah. Then you add that to this work in progress entry as in the update, and you add it to the right set. So it's very similar. Yeah? So the only difference being to update is the value is set to none rather than another object, and deleted is set to true rather than false. But basically, other than that, it's the same method. Yeah, so far so good. So these are all the methods you need from the outside: abort, begin, commit, delete, and read. And maybe we can then proceed to jump directly into some anomalies. Yeah, maybe start with snapshot isolation, right? What's the time? 5 minutes. So you see a couple of unit tests here. And basically what we do is we write down the schedules here. So that's a nice thing about that when you have, so when you look here, so that's what we call a schedule. Huh? Schedule, or sometimes it's called a history, but schedule meaning, okay, so this transaction, there's 2 transactions, and then they're interleaved in a specific way. So I'm saying transaction 2 has a begin, that's first, and then transaction 1 has a begin, transaction 1 then reads, and so forth. So we had that in the undergrad lecture at length. It's called a schedule. And what I'm now doing in Python in my unit tests, I do the same thing. I write down these schedules, which is super cool, because then I can really run the schedule. If you run your schedules on your keynote slides, not so sure that works. It's just one of my PhD students yesterday told me the story that now in the buses in Saarland, you have to show your QR code. Yeah, and one of my students didn't show the QR code, but just the card. But then the bus driver insisted on, no, you have to show me your QR code. It's more secure if I see your QR code. So it feels like the bus driver is trained to decipher the QR code and check whether it's correct. It's insane skills you have to have as a bus driver in Saarland, right? Impressive, yeah. And it's the same thing here, yeah. So of course I can run it with my skills, run these schedules, but there's so much potential to overlook things, in particular once the schedules get more involved. Yeah? So for these toy examples in the lecture, and you will see these examples in the assignments and the exams, of course, we all should be able to do that, but the potential for making mistakes is insane, yeah? And that's why it's so cool that we now can implement this stuff in Python, actually. Yeah? So we have these schedules here, and maybe check. Yeah, let me start with that one, because this test is more hardcore and more low level. This is basically a schedule, what you then see typically. Yeah? So I created transactional key value store. I initialize it with some data. Here, the only data I'm using in the test is a single object ID. And this put method bypasses all transactions. This is bypassing the transactional logic. This is just in the test to get going. Yeah, I want to make sure that the store has some data in it before starting the test. Yeah, but then the normal usage is what you see here. Then basically you see a schedule here. You see, there's a begin transaction from two different transactions. Yeah? So transaction, there's one transaction, ID 1 starting, ID 2 is the next to start. And then both transactions issue a couple of commands to the store. So here you see, for instance, that this transaction 1 reads some objects from the store under a specific where clause. Yeah? So the where clause is A = 7. So here I have relational data in the store, and here I only have this relational tuple consisting of two attributes. Yeah, this is, if you go to that declaration, you see that's A and B. So just relational data with two attributes A and B. And then this where clause is phrased against this attribute, yeah? And then it can be executed by the store. So basically, I do this here in the read objects method, pass this method, passes a where clause to the store, and then I get a list. I get a list of tuples that qualify. That is, on the one hand, that's the object ID of the tuple. On the other hand, that's the version of the tuple being returned here. Right, maybe we can debug that a bit, right? Why not? Oops. Yeah, I think that's, can I run the debugger here? Okay, so we wanted to debug that a little bit. So this is a schedule of two transactions, and now the first is reading from with a specific where clause, and then you get this initial list. I'll jump over that. And the initial list is just returning this just this one object. There's only one object anyway, so we can't get more anyway. But this qualifies obviously under the condition that A equals 7. Then I do a couple of inserts. Of asserts here. We can ignore this stuff, but then I create a new version, an instance of a new version under this condition, 7,8, and then I actually call the update method here with a new version. That's basically whenever we say in the schedule, we say write. If we go back here, that's the counterpart is now on the slides here. I did begin, I did read with this where clause, and here's another read. But then I do a write operation. On the slides, we not necessarily differentiate whether we update, insert, delete, or stuff like that. Here it's just always a W, yeah, for write operation, so changing operation, basically. So that's what I'm doing here. I'm updating the object, so the new version should now become the current version, at least from the point of view of the ongoing transaction. It's not part of the main database, of course. I run a couple of asserts and so forth and so forth. We can ignore that. This is a unit test. Then I reread it, and that's basically now the effect of snapshot isolation. So here, transaction 2 modified. If you go back, where's the update here? Transaction 2 modified this single object in the database. But transaction 1, if it reads the object, it must see the old object still. That is what snapshot isolation is about. That's the bubble stuff I mentioned several times. Yeah? And then I check that, hope for the best. Then transaction 2 commits. Yeah, then I check that the VIP entry is gone. This is work in progress entry. I have a new committed version. So the length of the list must now be 2. Yeah, if I look at this key value store, maybe do that a little bit here. Transactional key value store. Here are my entries. And for 42, I indeed have a list with 2 entries. Yeah? The first entry has a validity of start 0, and the other has a validity of start 3. That was this timestamp we drew in the commit method, an extra timestamp just for committing this transaction. The VIP entry should be empty. Yeah, that's what we're seeing here indeed. Yeah, then you reread here with the same clause. T1 still sees the old object because if it didn't see, if it saw the new object, this would be a repeatable, an unrepeatable or non-repeatable read anomaly. Yeah? We had that multiple times in the log-based protocols. So the transaction 1 reads the same objects with the same condition multiple times. Yeah? And a non-repeatable read means that you read it once, you see something, you read it twice in the same transaction, and then you see something different because concurrently some transaction committed. That's what's called the non-repeatable read anomaly. And this cannot happen here under snapshot isolation because you always see the snapshot. No matter what happens, it's always the same version you're operating on. That makes it, it's kind of a nice concept. It's a little bit, again, it's a little bit like Git. Yeah? You're on your feature branch. No matter what happens on any of the other branches, you don't see this stuff. This also comes with some problems because the more stuff that happens on the other branches, the higher the potential to bump into conflicts later on, of course. Yeah? But for the moment, you're in your bubble and you can ignore all of these potential conflicts. Yeah? You just look at the conflicts when you're in validation phase. Of course, or whenever you change something, someone else is changing, then you're blocked. That's the thing you see in your simulation phase, but validation phase might become tricky. Okay, where am I? Result reread. Yeah, now transaction. Let's try to commit transaction 1. This must fail because transaction 1 has read an object that has been modified and committed by another transaction. Yeah, okay. So that's basically a read-write conflict here. So I read something, and this is not going to work. So I hit play. Well, sorry, I hit play. Maybe enter here again. So we're back here. I wanted to hit this button. Okay. No, this old breakpoint. Here we are. Okay, we're back in business here. So we jump over that. That update is okay. But now, and this is syntax for, okay, I check in the tests that what I call here raises this specific transaction. Now if I commit the transaction, this will be raised because there's a conflict. So. And so forth and so forth. Here I start a new transaction, and then I check whether this new transaction now sees the committed, the newly committed version. This must be the case because the new transactions always see the most recent version of the database. It's the most recent main version in Git if you want, and that's exactly what's happening and what I'm testing here. Yeah, I think that's basically what you need to know here. Okay, with that, I think I removed the breakpoint. What else can we look at? Read-write conflict, snapshot isolation. Let's go to the store. Delete. Maybe we can look at read more recent commits. No, I think the read objects method. Maybe we can look a little bit at the snapshot handling. So how do we read snapshots? So this method will be called whenever you read something from the store, try to read something from the store. Yeah, okay, this is this helper method. Just have to remember my own code for a moment. So here I do that through an iterable. And what I do here is completely insane in terms of performance. Yeah, I know about that. So this is not efficient. And we will later on extend that and talk about ideas how to fix that. So the store I'm doing here is not using any state-of-the-art query optimization and processing. In a database system, when you execute a query, which means when you access stuff from a store, you should do some query optimization. You should do some clever things to read data. I'm not doing it here. I'm looping in crazy ways over the store, which is inefficient, just for the point of showing how this works. Yeah, but you can make all of this super efficient, in particular when using indexes and doing query optimization. No? So query optimization in the sense that you make decisions on join orders and stuff and predicate pushdown and all of these things is not so relevant here. What's relevant here is to use indexes, data structures that allow you to just access particular object IDs and not all of them. Yeah? So that's what you would do in a real application. So what I'm doing here is I loop over all entries in the store. Yeah? And basically, that's inefficient, I understand. And I get the visible object version under a specific timestamp. So the timestamp here is a timestamp which is equivalent to the transaction ID calling. Yeah, so if every transaction ID gets this timestamp, basically this ID, this is the stuff I can use for reading each and every time. And each and every time I read that, I read data with that version, I get the consistent version. It's the same as in Git again. You always get a consistent version when you use the timestamp for reading. Yeah? So I do it per object here, get the visible object version for this timestamp, and then I yield it here in this iterator. Maybe we can look at this method a little bit. So object ID, that's to be read. That is a version to be read. Okay, I do checks like, is the object ID even in the key value store? If not, I raise an exception. I have to check whether there's a work in progress entry. This is important because, assume a transaction changes data in its bubble. Now, if you read an object that was modified, you must return that modified object as well. Yeah, but only in the case if it was modified by this transaction. Not modifications by other transactions. That's illegal, yeah, because you're not allowed to see anything that was changed by anybody else. But if you're in your bubble and you change object IDs, then of course the next time you read the stuff, you should see your own changes. That's very important. Otherwise, you screw the logic of this. Yeah? And that's what's happening here. Yeah, so here basically we check, okay, is there a VIP entry? Oh yeah, it's not none. Okay, let's get that VIP entry here. Then we check whether that's equal to this timestamp. Yeah, so the timestamp of the transaction calling, then we directly return that entry because that is the entry that was created by this transaction that's calling this method here with this timestamp. But if that's not the case, then I basically have to select the most recent committed version that was visible for this transaction. So in the committed list, you have a number of entries with their start validities. And now you have to get the highest number in that list that's still smaller than the timestamp. Yeah, if the timestamp is higher than yourself, then that was committed by a transaction afterwards. Yeah, but maybe as you see it very well in this example I had on the slide. What was that? Here. That's too much edits here, though. Let's get rid of the edits. Okay. Yeah, so transaction 8, when it calls this method, get the current version or get the version I'm seeing for object ID 42, it must get this entry. because that's the entry transaction 8 created. If transaction 9 calls this method, it must get this one. Does it? If transaction 9 calls the method get the most recent version. It shouldn't be calling it, right? It's committed. Transaction 9 committed it. So the point is, if there's an entry created by transaction 9, that means transaction 9 committed. Transaction 9 is not allowed to touch the stuff at any point in time. Trick question. Should have spared that up for the exam. Sorry. No, it's on the recording. Okay, but so let's assume I'm just, yeah. It's louder.
You said transaction 8 is not allowed to touch or return?
No, transaction 8 is allowed. So there are two situations I'm seeing. Transaction 8 is calling, get me the version I should be seeing for object ID 42. Then transaction 8 will get this one. Yeah. If it's transaction 9 calling, the store should say, no, what the heck, you already committed, right? I mean, this is impossible. Any ID here, if you call with timestamp 1, 3, or 9, how is that possible? Because, I mean, it can't be the transaction that committed that in the first place, because it must have committed. If it committed, it's not allowed to touch stuff anymore. Yeah, that's the trick question part here. Huh? But assuming that you call, let's say you be a transaction 5 or something, yes? So transaction 5 is calling. So which entry is returned? Yeah, someone else? Yeah?
3.
Yeah, 3, of course, yeah? Well, if it's transaction, whatever, 12, which one is it? 9, huh? 9. So the highest entry in the committed list that's still smaller than the timestamp. That's going to be returned. That's the snapshot. The most recent version this transaction saw when it started. And that no matter what happens in the store, this version visible to this transaction 12 will never change from the point of view of 12, except it changes it itself, which in this situation is impossible. If 12 tries to update, delete, insert, it will be blocked because there's an 8. Yeah? So that's this white conflict being avoided. If 8 is calling, it will see 8 because that's the only change of 8. That's the only exception. You want to see the changes you did in your bubble. That's basically the semantics of the snapshot method. So maybe this is kind of this is actually an interesting again, I'm not sure whether I think I only said it 5 times so far, use asserts. I'm saying it a 6th time now, okay? Because this was where we screwed up in the implementation. Initially, we believe we had a check, and the tests were written like that we felt like, okay, the committed list is ordered by the transaction IDs. Basically, when the transaction ID started. That's not exactly true. Yeah, because it may happen that the transaction starts now, starts first. Do I have a schedule on that? Maybe I have it on the slide somehow. Let me check. Yeah, maybe this is a good example. Oh no, we don't have it here. No, I don't have it. But I can use that and maybe I can change that example a little bit. So if you look at this one, just because a transaction starts at some point in time, so this transaction 2 starts before transaction 1, doesn't imply that transaction 2 commits before transaction 1. So you could have schedules that transaction 1 starts after transaction 2, like here. However, it could also happen that this commit happens before this commit, like whatever, here for instance. Yeah? And then you have the effect that, okay, this timestamp associated here is smaller than the commit type snap there. Yeah, so basically be careful not to confuse the transaction IDs, which signal the start of a transaction, with a commit timestamp, which is used in the validity to signal from that point in time it was valid. That's semantically two different things. Yes?
Here, in step 4, transaction 1 always reads, right? So it cannot.
In step 1, transaction 2 only starts without reading.
No, I mean in step 4.
Yeah.
Transaction 1 reads, right?
Yes.
And for commitment, to commit, you need to change the version, actually write something, or
No.
you have just read.
No.
Okay.
But that's a great question. Maybe we can discuss that a little bit. So if I change the example like that, yeah, and she's saying, okay, transaction 1 only reads and then it commits. So what's the point anyway? It doesn't touch anything. So this transaction cannot have any work in progress entries by definition, because these entries are only created through insert, update, delete stuff, right? So, very good question. But what should I do about that?
If there is a single read, then there shouldn't be any issue. If there are multiple reads, then there could be an issue there.
Why is multiple reads an issue?
Because of the read-write conflict.
No. No, that's not true. So he's saying only if there's multiple reads.
Oh, no.
Yeah.
Because multiple reads.
Yeah. I mean, the weird thing is a transaction that only reads. What's the point of that anyway, right? I mean, let's just get that argument on the, hey, what the come on, hey, why do you do that anyway, right? I mean, okay, so there's an application program that's reading some data, but whatever that application does never finds its way back into the database state, because there's no update, delete, insert whatsoever. Huh?
It might make sense because, like, for example, when you're doing multiple reads that still need to work on, let's say, the same snapshot of the database. If there are multiple, like, you're doing multiple reads that will, for example, change the output to the user, but not change the state of the database.
Yeah.
You still need to have a consistent state of the database.
Excellent question. That's a fantastic question, actually, because you're alluding to how far, what is the space, what is the size of my transactional bubble? Yeah, so now you're arguing along the lines of the user interface. You're saying, the user is seeing inconsistent things, and maybe he's doing actions with another transaction based on the old state. Excellent question. Then you're screwed. But the database cannot guarantee that. Yeah, that's exactly the kind of discussions you will have once you start using the database in the UI. Yeah, so you read some data. Maybe you stop some transaction or you don't, yeah, but in both cases you will screw it up. You show the data to the user, commits the transaction, the read transaction, and then you make an action based on that with another transaction. So the old version of that transaction finds its way into the store, but the database has no way of knowing because it's two different transactions. Excellent question. Yeah? And that's what happens. And the problem is that this transactional concept ends at the boundary of the database system. Yeah? So the database system, I'm not responsible for that. I gave you that information. If you screw it up outside, that's not my fault. Yeah? So we can only argue about transactional semantics inside the system, within the transaction, across transactions, but not once you use UIs. And that's a huge issue in developing UIs. Yeah? So you bump into these kind of scenarios so many times, because whenever you replicate data, yes, you create a query result from the database system, you put it on some UI, and then you're screwed. Because you duplicated the data, yeah, so you still show the old version on the UI, whereas the database version is already changed, and then you have this outside change going in. Yeah? Anything may happen. Yeah? Excellent question. Yeah? So you should be aware of. So that's something you only see when you leave your database bubble and work with UIs. Yeah? But yeah, hard to guarantee that. I mean, what you could do, for instance, maybe let's talk. We talked about that a couple of months ago in my group as well. So one fix that you could do is, so when you read something from your database system, you say it, give it to the user. And now, if the user performs an action, you could try to, again with checksumming, you could do that. You could try to read the same thing again, and so make the read transaction part of the modifying transaction, and to check whether that returns the same result as before. Yeah? With that, you basically combine, you integrate this previous read operation into the changing transaction again. Yeah? That will fix it. But it's really advanced stuff. I haven't seen that in the UI so far, but yeah. Cool. Where was I? So we were discussing this read stuff. Okay. So basically, we're in a situation like this. Yeah.
One question with the code. Couldn't you make the territory index strictly greater? Do we need to have greater recall in this any your line?
These versions are ordered by the timestamp. Node entries must be ordered. There cannot be two entries with the same timestamp.
Yeah, so we should be able to make it.
Yeah, it could be greater because it's another invariant. You cannot have two entries with the same. That's true. Yeah, can do that. Mm. Okay, this is basically where we started with this question you had. So what if you're only reading? Yeah, this happens. You have read transactions. Yeah, this is the case, and the read transaction sees the snapshot, and this is a modification of the example I showed before. Yeah, so at some point, I think when we had that here, that's the example we used multiple times. So we really have something where we read some data from the database, and now we have the same. Maybe you remember I had the same argument in the undergrad lecture. And now I write something. And now the database system has a problem. It has no idea, same discussion as just before, whether this read operation influenced this write operation, whether the old version of the database state influenced what I'm trying to write. That's what I'm trying to avoid here. Yeah, and that's why I go into validation here and read the stuff again. Or did I see the old version? Tra-la-la-la. And if that's okay, then I commit. Yeah? However, if you change that to be this one, then transaction 1 becomes a read-only transaction. And for read-only transaction in MVCC, you don't have to do anything. Why? Because they don't influence the database state. Unless you run a separate transaction, but that's your fault and not mine. Yeah? So the database system, from the point of view of the database system, it's okay, you can't change the database state anyway. You're just reading stuff. I give you snapshot isolation. You will always see the same version. So why would I validate anyway? Because, I mean, there can't be any read-write conflict. If there's a conflict, other transactions will find out. But from the point of view of yourself, you're not influencing the database state, so you're good to go. And that also means that these transactions are kind of reduced to a point in time. The point in time when they started, basically their snapshot. They run in a point in time, whereas modifying transactions run in an interval from begin to the point in time when they commit. Yeah? That's their lifespan. A read-only transaction can be theoretically considered to run in the point in time. Yeah? So because they don't touch anything. Yeah? This changes as soon as you start writing. Yeah? We actually have a nice exercise on that in this week's assignment sheet that builds upon this. There's a nice question. Cool, great discussion. Okay, what else do I have? Yeah, maybe we can go through the slides a little bit. So again, we have these two algorithms. So the one I think I showed last time already. So basically, this is using checksums. Every read is pumped through a checksum, and then in validation, you compare whether this where clause, whether the read returns objects that yield the same checksum. If that is the case, everything is fine for this read clause. Yeah? So you have to go through each and every read clause ever issued by this transaction. And if that is cool, the transaction may commit. Yeah? Maybe briefly, if you look at the code, you see that in this underscore validate transaction method, and it's this first method, if I remember correctly. Yeah, we reevaluate all of the where clauses. So here it's called read clauses for this transaction ID. So we have this set, we kept it there. And then basically all the code that happens here is you read the snapshot, but now you use the commit timestamp. And this happens to be the most recent version in main. Yeah? So basically you're comparing your feature branch with main. You're trying to find out whether if you execute this where clause on the most recent version of the database, that will yield a specific list of objects and a specific checksum. And if that checksum differs from the one you observed before while running the where clause in your bubble, then you're screwed. Yeah, then you say, okay, there's a mismatch somehow. Maybe the object was changed, maybe another object was inserted, maybe another object was deleted. No matter what, there is some sort of conflict, some sort of change that so that you now differ from what you saw before, and then validation fails. That's the entire algorithm. Yeah? That's all you have to do. And then the second method is here you do the same for each predicate. So that's a different idea here. So you get the transactions that committed after TI started. How do I do that? How do I do the transactions that started after myself? No, that not started, that committed after I started. That's committed after TI started. That's the right thing. Okay, yeah. Yeah?
For the transaction that started, we have the start validity as the ID of this transaction. And in the list of committed items, we have all the committed timestamps that we can compare.
Yeah, there's an, yeah, maybe you could also do it like that, but there's an easier way. Any other ideas? Yeah?
You had in your code that you use the same method to generate commit ID for transaction, and that is commit that all transactions have greater commit.
A bit louder.
So all transactions with commit ID greater than your routine transaction
Yeah.
ID are the ones.
Yeah, but I want to know which of those committed. And there's a bunch of transactions that are running. So I start at some point in time. Some of them started before myself, and now they commit. So I have a transaction ID that's smaller than myself, actually. That's one case. The other case is they started afterwards and committed. Or there are some that started but didn't commit yet.
Their begin transaction ID is smaller, or their commit transaction ID is greater?
Yeah, okay, but you have to look at the list of transactions, right? Somehow, yeah. And in the code we do that through committed transactions log. Yeah, so we have a list of transactions that committed, and now when you start a transaction, I play a small trick here. So basically that's a list, and the assumption I make here, you can optimize that in many different ways, is I never delete anything from the list. Again, that's a point in time where you should reconsider and maybe prune that list and kick something from the beginning of the list. Yeah, if a transaction was committed and cannot influence anybody else anymore, you can remove it from the list, but you have to be careful with that. What I do here is, in begin transaction, I keep the index. I keep the index to the last committed entry in the log. So basically, if this length of the list is greater 0, which means there is already a transaction that was committed, I basically just return the length of the list minus 1. That is the last entry in the list. Yeah, so if that is my log of committed transactions, and now I start a transaction, I keep the pointer, in other words, the array index, to the last entry in that list. Yeah? If the list is empty, then I just return -1. And that's a trick I play, because while these transactions now are running, and while other transactions are committed, more and more transactions will be appended to the list. And that means when I'm back on this slide here, I can directly jump into this transaction log at that position, and everything afterwards is the transactions that committed after myself. I directly have the list. The tail of that log is the transactions that committed after myself. Yeah, that's how we do it in the implementation. Yeah, next step is to create a combined set of the objects IDs that were written by those transactions. That looks in the code as follows. Now we're in, not in this one. Why can't I collapse it here? Okay, whatever. We're in this method. We combine the write sets. So all of these transactions had write sets. All of these transactions modified certain object IDs. I just put them in one set. That's what I'm doing here. With this method, that's all I'm doing. So basically, this is the trick I just mentioned. So I look at the committed transaction logs starting from this position +1. So this syntax says, okay, what I'm referring to here is a list, a sublist of this list with a start position like this. Yeah? And I don't specify the end position. This means that what I'm referring to is a tail of that list starting with the first transaction committing after myself. And I loop over all of those transaction IDs, get the write sets, combine them into a joint write set. So if the combined write set is 0, there's no conflict. I can return directly, but that's typically not the case. So now I look at the read clauses, and within the read clause, I look at all object IDs. Danger, nested loops, complexity-wise, Houston, this may be super expensive. But then the main trick is I get the object version as of the snapshot. So that's basically here the timestamp. And I get the object version as of now. I do it here directly by accessing the last entry in the committed list. So high-level idea is I compare the object I saw in my snapshot with the object I'm seeing now in the committed list and check whether that's the same object or not. Now, if it's the same object, everything is fine. If there's a difference, then I have a problem. And then I re-evaluate the where clauses. So for all the where clauses, I now basically check whether the object as of then, the snapshot, is equal to the object as of now, as a committed version. If any of them returns the object, there might have been a conflict, and then I return false, so that means validation is unsuccessful. So maybe we walk through the pseudocode again to clarify that a bit. That's basically what I just showed here. So for each predicate of the transaction I'm trying to validate. So this T prime should actually TI, sorry, that's a bug. That should be TI, I'll fix that. So I'm trying to validate transaction TI. Yeah, gets a set of transactions that committed after TI started. We had that. Create a combined set. We had that. Okay. Now for each predicate I ever used in TI, and then for each object ID I see in the write set of the other transactions that committed after TI, I get these two versions. I get the snapshot version I saw, TI saw, and I get the now version. That is the object I am now seeing in the committed list, the last entry in the committed list. If those versions are the same, everything is fine. That's okay. But, so then I can continue if it's anyway the same version, because then these predicate evaluations would also yield the same thing. And now I evaluate the predicate, yeah, that's here, this P, on the snapshot version and the now version. And if any of them returns it, I abort the transaction. Because if any of them returns it, it means, okay, it was available then or now, if it's, or in both cases. So if the predicate returns the object, that means, okay, this object was changed by another transaction and it was visible under the predicate. So I saw it in the snapshot. Yeah, so if this returns it, oh, I saw it in the snapshot. If this returns it, oh, I see it now. So maybe I didn't see it before, but I'm seeing it now. So that's obviously a conflict because there's a new version of the data which should have been visible in the snapshot in the first place. Yeah, and so that's a check you do. And if you find that any of them returns the object under your read predicate, you abort. So basically what we do here is we check whether the predicates overlap with the writes done by the other transactions. Yeah? So there can only be conflict if the predicate range is being tested, return objects that were modified. And that's what I'm trying to find out here. So the predicates I used in transaction TI, did they return any object that was written by another transaction committing after I started? That's the check I'm doing here. Yeah? That's method number 2. Okay. Shall we go? Yeah, that's basically exactly the same code you see here as on the slide. Okay, maybe only 5 minutes. No, 7 minutes left, right? 8 plus 7. Okay, yeah.
Could you please describe the evaluate function again?
The evaluate.
Yes, evaluate.
Ah, so, okay, yeah. Sure. So else, combined write set, where was I? Aha, here, okay. So the evaluate function, maybe it makes sense to look at the API of that. So this is just the clause, and that's basically in mathematical terms a predicate. So predicate is a function that returns a bool value. Yeah, so a condition like a equals 42, you pass any object, say in our example it was a tuple with 2 attributes a and b, yeah, and then the object, this predicate returns either true or false. Yeah? Function restricted to return a Boolean return type is called a predicate. So those predicates are used for reading in the read method. Yeah, when we look at the where's my test transactional store? Come on. Test transaction. Also I have to leave this full mode. It's kind of test, begin transaction, test, and not basics. Here, for instance, so test update multiple. Where's my read method? Here, for instance, yeah? Read objects. So that's basically how the user of a transaction reads, passing such a clause, a where clause. In this here, basically here's an instance of that saying, okay, a equals 42, 43 for whatever reason. Yeah? So far, so clear? Okay. And then in the actual store, where's my store? I call these predicates. So I have a list of predicates. Basically, I loop over these predicates here. Where are my predicates? Here, these read clauses. So each read clause is such a clause. And then I just pass an object to that clause. Yeah? And then I check whether this object, so this if I call the predicate with this object, does it return true or does it return false? That's all I'm saying. Yeah? And basically, the idea of this entire line is to call it once with the snapshot version, that's this one, or the object version as of now. And the idea of this line is to check whether is there any discrepancy in the predicate evaluation in the two versions. Yeah? So would I see it? No, not is there any discrepancy? Sorry, that's wrong. is it returned by the predicate? In other words, does it overlap with that object? Is it either the case that the snapshot returned it under a read operation, or is it the case that I see it now with a predicate in the most recently committed version? That's what I'm trying to find out. Because if that is the case, I either saw it then or now, or then and now. It's also possible. And that's a problem, because then there might be a conflict. And that's the idea of this code line. Okay. Okay, maybe to wrap up a little bit, atomicity, I already explained that, but basically now, once we pass the validation phase, we have to move over the work in progress entries. Here we can't have a half-baked database state, and that's basically the things I showed you already initially. So committing means you move all the work in progress entries over to the committed lists and set all the work in progress entries of the transaction to none, such that other transactions can change them in the future again. And again, you want to make sure that you do that atomically, yeah, and don't validate and move over entries of two transactions at the same time. I mean, you could synchronize it again, of course, but here everything is serial in our implementation anyway. Aborting means you do not run phase 2, the validation, but you simply just do the second part here again. Yeah? You set all the work in progress entries of T to none without moving the stuff over, of course. Just throw the stuff away you touched without adding anything to the committed list. Yeah? So like that, none of the changes will make their way into the committed state of the database. Read-only transactions, yeah, we already touched. I think I can skip over that slide. So again, read-only transactions is really considered a point-in-time transaction. There's no validation phase, or you could phrase it like validation will return true at all times for read-only transaction. And we have a nice exercise on that, which is about an optimization of read-only transactions. Yeah. Python unit tests. I couldn't look at all of that today, but I invite you really to look at these anomalies a little bit, also to train yourself and understand the store. To me, again, this is a different difficulty level, and it really helps to understand the stuff. If you debug through these tests, yeah, and if you write unit tests, you always will find errors. Yeah, so it's really important that every developer writes unit tests. Never have a scenario where one guy implements and the other writes unit tests. You can do that additionally, but every developer, and even if the developer is called architect or super duper architect, you're not an architect if you don't write unit tests. Sorry. Yeah. So with that, see you next week.